Hey everyone, my name is Russ Sorrells, and I'm with CapEx Sales. We are located in North Carolina, South Carolina, and Virginia. And what we do is our number one mission is to add value to our customers. And so, in that spirit, we go live every Wednesday at 11:30, from 11:30 to 12, with an effort to bring value in the form of some learning, some lessons. Sometimes it's personal development. Sometimes it's topics like we're going to cover today that are specific to manufacturing and manufacturing processes, because that's what we do. We sell automation, leak test equipment. We represent ATC Automation, which Bob Faulhaber is from ATC. He's going to be sharing his wisdom with us today. We represent Cincinnati Test Systems, which is a sister company to ATC, but the largest leak test company in the world. We work with Duquesne. They do plastic joining, ultrasonic welding, hot plate welding, any type of plastic joining equipment is their focus. So as we move into today's IndustryCast, again, we always want to express our appreciation for the opportunity to serve you. If you weren't here, we don't exist. So also, as us being manufacturers representatives, if ATC Automation, the company in which Bob has worked for the last 9 years, doesn't exist, we don't have the opportunity to serve our customers. So we are grateful for the opportunity to sell and promote ATC Automation. So today, Bob Faulhaber is going to share with us, like I mentioned, he works with ATC Automation. He's going to share with us a better understanding of OEE and how we can calculate it. And the reason I love this topic, and I'm so excited about this topic, is oftentimes we'll get an RFQ or we'll get customers that say, we want a 95% OEE, or we'll want a 90% OEE. And it's like, well, you hate to say, you don't want to call somebody's baby ugly, right? Or tell them they don't know what they're talking about. But at the end of the day, you're like, man, that's not achievable. That is an unachievable goal that you have. So it just references a lack of understanding about how to calculate and conceptualize OEE. So Bob, with that, we'll leave it to you to help clear up all of those specific details, and we'll get your presentation going right now.
Great.
Anything to add there, Bob?
I can see it. Thank you, Russ.
All right, here we go.
Great. First of all, good morning, everyone. I'm pleased to be with you this morning to discuss overall equipment effectiveness, better known as OEE. This equipment measure is very widely used, but is often misinterpreted and frequently modified by both the equipment user and the equipment producer. I'm going to describe the classical elements of OEE that we use at ATC and are the most widely used measures that comprise this calculation. So next slide. Let's start with the elements of OEE. By definition, overall equipment effectiveness is a statistical tool that combines three different manufacturing process values to provide an overall performance measure for the equipment. And it's an interactive process. Each of these values, these ratios, interact with one another. And I'll describe that a little bit more as we go through. The calculation is very simple. It's the availability ratio multiplied by the performance ratio multiplied by the quality ratio. So it's three values multiplied by each other. Seems very simple, right?
Well, I don't know. I don't
it gets
know,
a little bit more.
Yeah,
it gets
ratios are, Bob. So I'd say no, it's not simple.
So let's talk about the availability ratio. It's also known as the uptime ratio. This is the amount of time that the line is actually running compared with its available time. So it gives you a ratio of the uptime. It'll be in the form of a percentage. And these ratios can be in the high to mid 90% range. So that's
okay. So let's talk about that right quick, Bob, if you will. So we've got 24 hours in a day.
Mm-hmm.
I can't remember, 28,000 seconds in a day or something like that. But you've got, so then based on the amount of lunch downtime they have, right? So that's planned.
Right, yeah.
And then your breaks that you're going to have on top of lunch, and then maintenance downtime would be calculated in that. So some of it's planned and some of it's unplanned, but all of that goes into calculating the availability ratio.
Well, actually, you remove the scheduled downtime from the total time to give you the available time. And I'll go through that. I have a diagram actually that shows you what we do there.
Okay.
But
All right,
we only use the available time. If you have a planned downtime action, let's say it could be preventive maintenance, where it's planned, that machine is planned to be down, or you have meetings scheduled, lunchtime, break time. Often
do people do preventative maintenance, Bob?
I hope so. So there's those are scheduled items that you remove from the calculation because it's not available to actually be up and running. So that's out. But any unplanned event that causes the machine to stop is considered unplanned downtime. So that has to be included in this calculation. Some examples of these would be, and this is an interesting one, changeover and setup times. Actually, this is typically a changeover or a setup is typically included as a planned event because our customers, all of our customers will plan when we have to shift over to another type or product type or whatever it may be.
Mm-hmm.
So they'll allocate specific time. However, let's say we have a planned changeover time of 15 minutes, and that 15 minutes is removed from the available time. However, let's say instead of 15 minutes, it takes the team that's running that line 30 minutes to change that line over. So that unplanned changeover time is included in the downtime calculation because it was more than what was originally, and it's an inefficiency. They did put in the time period that it was allowed. So that's a legitimate deduction from available time.
Wow. So this is a very disciplined, you got to be very disciplined in order to calculate this on an on-time or regular basis, right?
You do. And we try, and we have a worksheet. We try to, and a lot of I would tell you now that a lot of our controls engineers are very good at being able to plug these into the software on the lines. Mm-hmm. A live OEE figure calculated here. But we're going to go through the manual process and I'll show you a worksheet that allows us to step through it and show you each of the pieces of the
wonderful
you have to go through. So some other examples are equipment faults. That's probably a very significant, oftentimes, part of downtime on a machine, especially when it's in the early stages of debug and launch. Lack of parts or lack of operators. You know, if you don't have an operator that was supposed to be there and is not there, that would also be considered a legitimate unplanned downtime. So that's the availability ratio calculations. The performance ratio is also known as the cycle time ratio. And this is the difference between the design cycle time of that piece of equipment versus the actual cycle time for that piece of equipment. So an example of that would be, we just took a measurement on this line and we've determined that this line is running at 30 parts per minute. But the design of that line was 33 parts per minute. So we're running at some percentage lower than 100% of the speed. So in the first item, we're identifying how much of the available time is the line actually running. In this second value, we're measuring, okay, while it's running, how fast is it running based on the design of that equipment? Is it running at the right speed?
Is that like one cycle that you use as your point of reference, or do you have over a period of a duration of time?
You do it over a defined period of time.
And what is that typical defined period of time?
A typical defined period of time would be a shift of production, 8 hours of production, be 10 hours of production, but it would be a defined period of time.
Wonderful.
Make sense?
Yes, sir.
Okay, and that's the performance ratio. Some of those would be, for instance, machine wear. Now, that doesn't come into play when you have a brand new piece of equipment. Of course, machine wear is not there. If it is, we have a problem with a brand new piece of equipment. But it does come into play. And if, let's say you want to conduct an OEE evaluation of a machine that has been operating for 5 years. So you want to look at the OEE now after 5 years of runtime versus what it was at the beginning. So that in that particular case, machine wear is an issue. So that could be a possibility of affecting the performance or speed of the machine. Substandard parts, let's say, for instance, you have a feed mechanism that's feeding a plastic component, and one of the cavities for that plastic component is allowing flash to occur on the part. So in the feed mechanism, as that part is marching down the track, it's not going as fast as it needs to get to the nest in time to be placed on location. So what generally happens is the machine waits for that part to go into the nest and then moves on. So that could create a slowing of the speed of the equipment. And then another important effect on speed would be operator inefficiency. If the pace of this piece of equipment is governed by the operator, for instance, an operator is placing parts in a nest and then engages the machine to cycle, that speed, that if that individual is learning the job for the first time, or for whatever reason is not as efficient, then that will also slow down the machine. So that's an assignable cause of the speed loss of the equipment. So we've looked at how much of the time is the machine actually running of what's available. We've looked at how fast is it running during that period of time. And now we want to know how many good parts is it producing. And this is the simplest of all calculations. It's basically the number of rejects divided by the total number of parts produced to get a percentage of good parts. And so that's a pretty straightforward calculation. That's part of it.
So all of these need to be done in that certain that duration of time that you've defined.
That's correct. All of them,
okay.
all of them apply to the same period of time.
Yeah, because if they didn't, then
parts.
Yeah. Okay.
Right.
Wonderful. Thank you.
Mm-hmm. Yeah. For instance, on a new piece of equipment, a typical runtime for us for an FAT, a factory acceptance test, is an 8-hour run. So that will be our defined period of time, and we'll deduct any unplanned any planned time first, and then we'll count all of the unplanned time that the line is down over that period of time, over that total period of time.
Okay.
Okay, good. So this next diagram identifies the steps in determining OEE, and it also highlights how these three measures impact with one another. And that interrelationship is a very important part of it, and it's what drives that end number. And I'll talk about that in the next slide as we go through. So the first thing we start with is a shift. I'm going to use a shift of production. Could be 8 hours, could be 10 hours. I'm just going to say the total time we have is one shift of production. Before we do any calculations, we first have to identify what do we have planned to be down over that shifts of production. So we take that total shift of time, let's say it's 8 hours, and we have 15 minutes of scheduled maintenance, maybe a changeover in there as well. We have 15 minutes. So our available time now becomes the 7.5 hours, or 7 hours and 15 minutes.
Well, yeah, okay. And so they look like that. Just to drill down on that, if you go over to lost causes, it seems that the next one is the running time, and is that where you take into account changeover setups?
Yes, yeah, it shows up in there. Yeah, the first time, all we're doing is identifying the available time
Lunch
in that shift.
Yeah.
Yeah, for that
Okay.
one shift. Now we're going to take that running time, that available time, and we're going to deduct any downtime that's deducted from them. If you look at that chart, at that bar, that red section in that running time bar, that's the downtime that comes from the total available time. If you'll notice, if you look up from there, I don't have control of the arrow, Russ, but it aligns with the available time. So that downtime is what's being deducted.
Yeah, so this is the whole shift.
Right, so that's for that one shift, correct. Now the next measure is the performance ratio. And what we're going to do here, this calculation is a complex one. I prefer not to use that. What we're going to do here is divide the design cycle time by the actual cycle time. So if the actual cycle time was 33 parts per, I'm sorry, 30 parts per second, we have to divide that by the ideal cycle time to get to percentage of the speed that the line was designed to perform to. And that's speed loss. You see that red section there is actually the speed loss that we've lost from that available time. And then the final calculation is out of all the parts that we produced, how many of them were scrapped, and what's left is the good production. So that's the scrap rate or the quality rate of the equipment. And if you look at those three red sections, those combine to generate the total loss capacity of the line. So, and that's where the OEE calculation comes into play. So what should the OEE value be? This is an area where, as Russ mentioned, it can be a little bit contentious. And we have to calibrate ourselves to the way this calculation works. In the engineering and manufacturing, we're really focused on statistical performance measures, and we're used to seeing Six Sigma values at 99.99% of the population. And oftentimes we think, well, that applies to OEE. It's the same thing, but it really is not. This is more of a reliability measure where if we have the reliability of a total system, it's the product of each individual subsystem. So the total reliability can never be as good as each of the individual reliabilities. So the way this, let's look at an example. On shift one, we had an availability ratio of 90%, not too bad. So that means 10% of the available time, it was down for a various number of reasons. We had a speed ratio, a performance ratio of 95%. So it was running at 95% of its ideal speed on the line. And then quality, we had 99.5% of the parts that were produced off that line were good. So now if we take 90% times 95% times 99%, you come up with an OEE of 85.1%. So even though we have values for each individual measure in the low to mid 90s, that OEE calculation, after we multiply them by one another, is now only 85%. So that's why we see a number like 85% when we're running specific individual values much higher than that. It's because they interrelate with one another. So a good standard for OEE is 85%. That's a number that at ATC we typically identified as a
world class. Is that
world class? Yeah, it's not uncommon for lines, especially older lines, to be running in the 50 to 60% OEE range. So this is a number that we would expect to be world class within there. There's some things we have to be aware of, and it's an important part of this calculation, is that we have to be aware that there are a lot of variables that affect this calculation. Even though the calculation is very simple, operators, parts, changeovers, and a lot of metrics that may not necessarily be within the control of the equipment manufacturer are also part of this calculation. So the best OEEs are developed when the equipment producer and the equipment user collaborate effectively with one another. And we talk about what the parameters are going to be, what the values are going to be, and everybody understands and works together to make sure. In the end, the bottom line is we want to identify where there's opportunities to improve and assign the causes to those improvement opportunities, and then work on correcting those going forward.
It seems, Bob, and correct me if I'm wrong here, that if you were going to measure OEE, you would want 6 months, 8 months, 10 months, 12 months of operation on your brand new piece of equipment to really understand, because by then your operators are trained,
Excuse me.
your product flow into the equipment should be sufficient to
Right.
to do that, and then any bugs ideally worked
Right.
out of the equipment, so that it's not have unnecessary stoppage because of a part.
Right. You're absolutely right, Russ. It's a very valuable tool to understand how your line is performing, and also to evaluate the effectiveness of your preventive maintenance, your training of the individuals, if it's an operator dependent operation. All of that comes into play, and it should not just be a value that the equipment manufacturer uses at FAT. It should be a value, a calculation that's used throughout the life cycle of that piece of equipment to understand how it's performing going forward.
Yeah, that's good point.
And sometimes over time, because oftentimes the equipment manufacturer may not necessarily see every source of variation, but over time now those sources of variation may come into play, and it provides an opportunity to get better. So there may be instances where the OEE actually goes up, not necessarily down, because of experience and little minor improvements over time that make the equipment more and more effective.
Yeah, and that's what you would expect, right? And so in the beginning, it's going to suck. I mean, it's not going to suck, but it's not going to be great. It's going to be much more up and down from day to day, as opposed to consistent after you get that regular operation in.
So this last chart, this is a worksheet. It's a simple Excel worksheet that we use at ATC to manually calculate OEE. As I mentioned earlier, a lot of our controls engineers now are actually incorporating this measure into the software for the line, so we don't have to, you can get it at any particular point in time. But to do it manually, I think it's important to understand where the numbers come from. And I plugged some numbers in here so you can see how the calculation occurs. We have a total shift time in this particular case of 480 minutes. We have scheduled or planned downtime of 48 minutes. And while we were running during this period of time, we had unscheduled downtime of 35 minutes. And we've also calculated, now we take the total shift time minus scheduled minus the unscheduled downtime, and we get the total operating time of 397 minutes. Now we have to perform the availability calculation. So the first thing we do is take the total operating time. This is what actually, this is the actual operating time for the machine. And we divide that by the total shift time, but we deduct the scheduled downtime. See, A minus B. We take that scheduled downtime out. So we have, again, the total actual operating time divided by the available time. And the available time is the total shift time minus the scheduled or planned downtime. So now we have a calculation of 91.9% with those particular values based on the performance. So before we can go to the next value, we have to identify over those 397 minutes, how many pieces of production did we actually produce? So we actually produced 11,993 pieces. And we know also that based on the design of that equipment, or perhaps the requirement of the customer, that this machine is supposed to cycle by design at 33 pieces per minute. So now to perform the calculation, we take the 11,993 pieces, we divide it by the runtime, so that will give us the actual cycle time of the machine, which is around 30, I think. I should have put that down there to make it a little bit easier, but it's in the vicinity of 30 pieces. And now we take that number and divide it by the ideal cycle time, and that'll tell us what percentage of that ideal cycle time we're actually running at. What is the speed of the equipment?
And it was 30.2.
30.2, okay. So, and that'll give you, if you do the calculation, it's 91.54%. That's where that number comes from. And then the final number is a pretty straightforward number. We take, this is the number of rejects or scraps that we produced. Out of those 11,993 pieces, we scrapped 389 of them. So the calculation is, we take E, the 11,993, minus 389 pieces that we scrapped, and then we divide it by the total production, and that will give us our quality rate, which is 96.76%. So those are the three percentages or ratios that now we're going to plug in to the OEE calculation to get our final OEE. So we have 91.9% as an availability rate, 91.54% as a performance rate, and 96.76% as a quality rate. We multiply those three times each other, and we come up with an OEE of 81.4%. So that's how the calculations work.
Wonderful. So I have two questions.
Mm-hmm.
One is, would you be willing to, if any customer says, hey, I'm interested in that spreadsheet, would you be willing to share that?
Absolutely.
Share this?
Sure.
Okay.
Absolutely.
And then the second question is, as I think about a line has 10, 20 stations on it.
Mm-hmm. Mm-hmm.
So do we then go down to the station level and do the same evaluation at the station level?
Yes, it's a great question, Russ. Let's say we have a pallet assembly line that's got a dozen discrete stations, and they're linked by a pallet, a conveyor line that moves a pallet from one operation to the next. The first thing we're going to do, I think this is a better way to do it. The first thing we do is we look at the overall OEE of the line, and that is the starting point for us.
And so just to confirm that, that's the parts coming off the end of the line.
That's right. That's the part.
We're
exactly right.
Coming off the end of the line, we're packaging them up, we're shipping them to another department, or shipping them to our customer.
Right. That's exactly right. Yeah, that's what is the overall line OEE is calculated. Now we'll come up with a number, and let's say it is 81.4, and we want this number to be 85. Now we have to drive down to where are the assignable causes? What caused this number, this end of line number, to be 81.3, 81.4%? So now what we will need to do is to find the OEE of each of the individual stations. And in that particular case, then we're looking at the output just from that station. And it's exactly the same thing. We do the very same calculations, but now it's in a more discrete element of it. And we may find that there's one particular station that's affecting the output of the whole group.
Right. Yeah, and that's what I was getting at. It's kind of drilling
that's
deep.
Exactly right, Russ. Yeah. So it's not just a one-shot deal. You can't just do it once and say everything's good. You have to really you have to dig down, especially if you're not performing at the rate you expect the machine to rate.
this seems like a very disciplined and intentional way to evaluate the effectiveness of your equipment. How often do companies go through this process? Should they? What does a world-class organization
Yeah.
do from your experience, Bob,
Yeah,
to measure this?
Yeah, that's a good question. Thanks. This is the most widely used among our customers. This particular, it's why I call it classical. The majority of our customers use this very same calculation, and it is in their performance specifications. And it's in there. Many of our customers take elements of it, and they say, I want it to cycle at this rate, and I can't have more than a 5% reject rate. And they give us discrete performance measures, but they don't necessarily put them together for an OEE. And I'd say there's probably a quarter of our customers don't actually ask or require an OEE. They look at just those discrete measures all by themselves.
Right.
For them,
Yeah,
that meets their priorities.
How often do you say the goals to hit 85 and then you're like, okay, we hit 85 and we move on? Or do they measure this once a quarter, once a year? What is the frequency with which?
It's our recommendation is to use it on an ongoing basis as an evaluation tool, as part of your predictive maintenance. Perhaps it's an excellent tool. It's really a very simple tool. Once you get used to collecting the particular pieces of information, it's a super simple tool to get a real life measure of how the line is running over time as well.
Yeah, it seems like it can be tremendously helpful.
Yeah, we do this, we all do this in the production environment for dimensional characteristics. We have CPs, CPKs, PPKs that we look at on the dimensional characteristics, because those are so important to the end customer as well, our customer's customer. But for our customer, not necessarily the end customer, for our customer, this is very important because it's a measure of how effectively they're utilizing the equipment.
Excellent. I think this is so helpful. Hopefully others get the same benefits that I have gotten from you sharing this with us, Bob. I'm really
Thank you.
Appreciative that you've taken the time today. Anything else to add?
No, I thank you for your time, and I hope it was helpful in getting an understanding of what OEE is all about.
Yes, absolutely was. So as we always do, again, want to end with letting all of our customers know how much we appreciate the opportunity to serve you on a day-to-day basis. So again, we don't exist without you, and we're just grateful for the opportunity to continually be adding value, and we're proud to be able to represent these wonderful companies that we do, including ATC. Thank you, Bob. Appreciate your time.
Thank you.
See you, everybody.